let's kick off because I loved the fact that I get to hear all of you, and I got a sense that there were some differences of opinion. And maybe we can start by exploring those differences of opinion and building on that. So let's start with the question of Moore's law. Like I think, Simon, you said that Moore's law was dead or dying rapidly. And James had a view it's going to run for another 7 or 8 cycles. And Cass, I'm sure, has a view on this as well. Tell us, what's happening with Moore's law? What's your take?
So Moore's law is a bit of a confusion. So there have been 2 intertwined laws that have driven the evolution of silicon. One's Moore's law, and one is called Dennard scaling. It's Dennard scaling strictly that is dead. So Moore's law says we keep shrinking, we fit more stuff on a chip, and it is economic to do that. And I think I said that continues for maybe a few more generations. We probably get another 3x more utility out of that in terms of performance. It's the Dennard scaling bit which is dead. That's the bit that says you have to keep dramatically reducing the supply voltage in order to prevent those crammed in from components from getting too hot. Now, when people talk about Moore's law and they're not in chip conferences, usually they mean both of those. So when I say Moore's law is dying, it's kind of a mixture of the two. Actually, we have some more shrinkage to go, I get that, but we don't have any more benefit from the power. Well, we have a tiny bit, not very much.
James?
Simon, don't you need Moore's law to go more than just 3 cycles since you guys are a silicon-based company?
Well, I think whether it will go more than 3 cycles is a bit moot. So when Moore's law was first proposed, the doubling time frame for number of transistors per square inch was 12 months. And then it was reinvented a few years later, 18 months. And then it was reinvented again at 24 months. And now it's actually about, well, most recently it's been about 2.5 years, as I showed you on that Xeon plot, roughly 2.5 years per generation. I think right now, looking forward, it's probably about 3.5 years. So actually, it's never been a constant law. You know, that's mythology. It's actually an exponential. It is gradually asymptoting off. Now, the hard thing about an asymptote is saying where it's finished.
Fair enough.
It just gets progressively more expensive.
So Cass, do you have a view on this?
Well, I think these are, am I on?
You might be turned off there.
I think I may be out of batteries.
Okay.
I don't have a light.
Maybe we can get a roving mic to Cass. Yeah, sorry about this. The heat is draining the batteries as well. You've been smart wearing a t-shirt, showing your guns off.
Check.
Guns,
okay.
right.
I think, so the distinction between Moore's law and Dennard scaling, I think that's kind of spot on, that people tend to mix the two together, and that's a great description. It is also an economic phenomenon. So even if, kind of there's laws of physics, but then there's just things becoming more expensive, it's clearly becoming more challenging. I guess I would say to your last slide of kind of looking at these new substrates and so on, I totally agree. And I would include kind of innovations within silicon in that also. So, I think light is very interesting. But silicon itself, there's still some room at the bottom, I would say, to do.
Plenty of room at the bottom.
Yeah, exactly. Yeah, and so luckily I've been privy to meet some of the folks at Intel who work on the kind of the process side, and as you can imagine, these are some of the most closely guarded secrets within Intel. There's some interesting kind of skunkwork stuff going on there. I'll just leave it at that.
So don't write Intel out of the equation just yet.
Yeah.
So I'm curious about this. We've moved from a world where, if you go back 20 years, we only really had one type of chip anywhere in the world. It was the general CPU. We now have a handful of new things. Do we think that continues as a Cambrian explosion? So if we look out 10 years, there will be dozens of different chip types abstracted by software, or will we see a consolidation back to 1 or 2 architectures? I want to know who wants to take this first. Perhaps Igor, you want to take a view on that?
Well, I'm just going to make a small remark on the Moore's law.
Okay, fair.
I think a little bit what we do at LightOn is a little bit hinges on the fact that whatever is done before and whatever is done afterwards essentially serves on Moore's law. There is a type of conversion between photons and electrons back and forth essentially serves on that. So as long as it continues, but we're still far away from exactly where we are right now at the electronics level. But a kind of new architecture that could be popping up essentially are already also surfing on Moore's law from the very back, and they are essentially improving mostly because Moore's law has essentially shown the path in that respect. So we are not probably using the 7 nanometers type of computations that are being done nowadays. But I'm more thinking along the lines that, a little bit like others said, that we're going to see some sort of hybrid architecture. But the hybrid architecture and whatever other type of computer that you're going to have on the side is going to be using and it's going to be leveraging what you have had on Moore's law so far. So to a certain extent, I think we're going to see this thing continue on, mostly because we're going to be able to offload specific type of functions outside to go back into this thing. So.
Yeah, so that sounds like there will be other types of chips and other architectures kicking around, though, in some sense.
In some sense, yeah. I mean, I'm looking at optics, and from the early 60s to about 1994, optics was essentially something that you could actually use, mostly by the military, to actually do things. This whole thing just went dead as soon as the Pentium 484 essentially came out, and from that on, nobody looked back. So all I'm saying is, there has been winters in AI. There has been at least one winter in optical computing. There's going to be a new beginning there as well.
Simon, what about your view on this? Lots of different types of chips, or is kind of Graphcore's IPU going to be chip to end all chips?
I think the one thing that I would point to from the Graphcore IPU point of view specifically, and then I'll answer the more general question, is that, as I said, as we go forwards now, power density obliges you to basically fill logic chips with memory and not logic. Now, as we march forward in Moore's law, you get more and more transistors. You have to use those for memory. It's the only thing that you have the power to drive. So the Graphcore, the IPU viewpoint, I firmly believe, gets better with the rest of Moore's law, whereas the GPU scenario gets worse with the rest of Moore's law. So I hope we're just about late enough to be competitive, but as we go forward, we'll become more competitive. The more general thing, I would actually take issue with the statement that the world has been dominated by one type of processor. Actually, most of the processors in the world and most of the economic flow from selling processors has been in DSPs, signal processors, not CPUs. Your smartphone, for example, the thing that does the communication is not the ARM cores that also exist on your smartphone. They don't even run the protocol stack. They just draw pictures on the screen. And in fact, many of them, they don't even draw pictures on the screen. That's done by GPUs. So CPUs, I mean, we talk about them a lot. They've been around a long time. DSPs are a derivative. IPUs are a derivative. TPUs are a derivative. Everything's a derivative of the same basic von Neumann machine. But in terms of diversity, economically driven diversity, actually, through not the past decade, it's been quite quiet, but the one before that, there was a massive Cambrian explosion of things in embedded products that mostly you don't see because they're sold for cheaps. You see them now because it's exciting and they're huge and they dissipate massive amounts of power and they have 23 billion transistors. And
Right. But I'm curious about the Intel perspective on this. How do you look out over the next 10 years and you look back into this and say, what are these chip architectures going to look like? Are they going to be dominant ones or diverse ones? Or Cass's view, if that's safer for you. Yeah.
No. I think I'm trying to figure out where's the cutoff between a few and many, because
Right.
There's going to be more than one. Will there be 100? No. So already there was in the last talk we had this kind of matrix of inference, cloud, edge, and training, cloud, edge. Right, so there's already going to be different. An inference chip looks different than a training chip, when you really start to kind of customize it for particular use cases. So there's already kind of a bit of a bifurcation there. So yeah, my kind of gut feeling is that there will be a diversity. The question, I think, is a little bit about how these things are going to be packaged. So if you think I think the Cambrian time was maybe when there was, you started to have sexual recombination between organisms, right? So you have mutations, but you'll also have crossover in the sense that, you've seen it a little bit with Volta, where the tensor core kind of migrates over and gets embedded in the GPU I think there'll be some more phenomena like that, where bits of IP kind of find their way in different entities. You know.
James?
I have questions for
Well, before you give me a question, let's
I like to hear the perspective of Simon and Kaz, since both of you guys are building basically TPU-like things or chips that will do deep learning better, and both of these, your latest chips have come back from fab. I guess my question is, what has surprised you on the upside? What's turned out really good and really positive, and what has been a little bit more challenging? Maybe Simon.
What surprised me about my chip after it's come back from fab? Nothing, fortunately. It does what it's supposed to do. I suppose I am perpetually surprised that fabs can make stuff that complicated and actually get pretty much all of it to work, at least within the radius of our ability to build things that repair themselves. Okay. So I'm always surprised by that, but I'm not really surprised by anything else. I do think that there will be a Cambrian explosion, because I think this is the single most important technology shift we've ever seen, like I said. And that's a good reason to try lots of experiments. Lots of them will fail. So I think we'll see all sorts of different ideas, and many will die out, and we'll end up with a few, but not one.
Nirvana chip?
Yeah, so I mean, we had we got parts in late 2017. We've shared them with partners. It's the same kind of response. But I joined post-acquisition, but
you want to say this is the acquisition of Nirvana. Do you want to say something, just 20 seconds on what Nirvana did and why it was special?
Yeah. So Nirvana is a startup with 3 folks that I worked with at Qualcomm who left and thought that, hey, let's build custom hardware for deep learning back in 2016 or so, 15, 16. So they kind of did that, and they had some designs, and then they were bought by Intel, and now as part of that acquisition, there's still the chip roadmap to fill out, but we're also, that acquisition turned into what Intel's calling the AI products group. So kind of both the chip roadmap and also providing some overall leadership within Intel around AI. Yeah.
Okay.
Now how's the chip?
Yeah. So, so again, because working with the folks who did the initial design, they're all like, "It powers on." It's like it is kind of a miraculous process to see
every time
to see your baby come back. It wasn't my baby, but it was their baby. I could see this. And then recently at the development conference, we reported some results of just very high utilization rates on the. It's a little bit different from a TPU in the sense that it's a linear algebra processor. It's not a systolic array.
Oh, I see.
So, there's some subtleties there, but we're very happy to get the utilization very high. Negative surprises, I would say, none.
Now, I'm curious about the dominant player in the AI chips at the moment, which is Nvidia. And the thing that has struck me is that in the last few weeks, some people have run some benchmarks comparing the Nvidia cores available through AWS with the Google TPU cores available through Google Cloud Compute. And the thing that was surprising was that essentially the latest NVIDIAs seem to do as well as these dedicated processors. So a question that I have is, at the end of the day, NVIDIA is aggressive, it is well-funded, it is moving fast. It sees the world in terms of the demand cycle, as well as the rest of you do. What will it take for independents to actually, or new entrants into the market, right, actually take to overhaul NVIDIA's current lead, the lead they've had over the last 3 or 4 years? And James, I'm going to ask you to answer this one because you look at NVIDIA first and then pass it around.
Yeah, I worked at NVIDIA for 9 years, and it is the most ferociously competitive company in the world that I know of. Intel's Andy Grove had a famous adage that only the paranoid survive, and they're known for being paranoid, but Jensen's team, like competing against NVIDIA in the 90s was hard, but NVIDIA was kind of a small, medium-sized semiconductor company back then, and they crushed. They're the only survivors in the 90s gladiatorial combat of all those logos you saw on the slides. Today, NVIDIA is 10, 100 times larger, and you're not competing against a second-generation CEO or someone who's a professional caretaker for the company. You're competing against the same founder CEO who basically did all that carnage back in the early 2000s. So I think it's extremely hard. Last year, I thought these TPU designs had a chance, because on paper, it's very clear. NVIDIA deploys all these transistors on HPC, on gaming, and if you just redeploy those transistors on deep learning, you should get 5 times performance. The Google TPU results you pointed out, Azeem, is kind of cold water on that, right? The chip came back, all of the transistors are for deep learning, and it's not faster. Why not? I think it really draws into a question.
I know somebody who might have an idea.
That's quite a complicated story as to why that occurs, but I can assure you that the IPU is faster. And we have released a few early benchmarks. I won't kind of add to those at this stage, but we will very shortly. But we've shown early benchmarks where, in some cases, for some certain types of recurrent network, for example, just having the locality of memory on the chip allows you to have 2 orders of magnitude improvement in performance, 200 times improvement in performance of a chip that's the same size, costs the same amount, burns the same power. So certainly new architectures can do different things. Now, there are also other areas where actually we have some advantage, but it's not huge. So it's very difficult to be brilliant at everything. And I think that's probably the answer to your question. We are, in this market, in the capability or exploration phase of a whole new opportunity. Nobody is bothered about efficiency. This is fantastic for new startups. Because our customers say to us, we don't care what it costs. We don't care how much power it burns. We don't even care if we have to rewrite our software in your wacky language. We haven't got a wacky language, by the way, but if we did have, they wouldn't care. They just need to know how to drive a car before that guy. Otherwise, their business is dead. It's existential. Now, once they've worked out how to do it, of course, then they'll go into an efficiency phase, and then they'll want it for $50, and et cetera, et cetera. But right now, the world is wide open to all sorts of experiments, and there's no economic advantage, therefore, of being big, which is where NVIDIA get their muscle from. Lots of things will be tried out. Some of that stuff will work. And if it works, it'll be driven into a market presence before we get to the efficiency phase when the economics cut in. Hopefully by then, we will have grown to a scale where we can match up to behemoths like NVIDIA. I did sell my last company to NVIDIA, by the way, so I have been inside the beast for a while. I know how Jensen works. I know how we work differently.
Fantastic. We've got time for one more question before we move to the next speaker. But the question I wanted to ask was that in the morning we had a lot of people talking about the frontiers of the research and the systems level questions. One thing that came up was that we're making a lot of hay with deep learning and have been for the last few years. But increasingly, people are starting to say we need different approaches. To what extent are the current families of chips future-proofed against whatever those new approaches might be? And we have some idea, and there are other ideas we don't have. And to what extent is it even possible to build some kind of new chip that will support algorithmic approaches that are not these sort of vanilla deep learning? And maybe we'll just start with Igor and work our way down.
It's a very good question. I think, as you said, there is an explosion of creativity. I mean, there is no other way to say it. If you go to NIPS, to one of these conferences that are essentially where the top minds are essentially talking to each other, you see that there is really this creativity that you just did not see before. And I think a lot of the hardware folks are just trying to catch up on those things. I mean, you can see that in different ways, but they're always catching up 2 or 3 years later, trying to match those things. But then by the time they're trying to catch up, they're always, oh, okay, but we're like 2 or 3 years already late. So I think it's very exciting in that respect. For us, one of the bet is to say that you have to do something that is universal. And then somehow somebody's going to pick up on this. Mostly because irrespective to the algorithm, you're going to be able to actually use this thing at some point in time. So that's the way we are looking at it. But I mean, to a very large extent, this creativity thing that is going on right now is very unsettling for anybody that is in hardware. That's for sure.
Cass?
Yeah. Yeah, future-proofing is something that I think about a lot. It's kind of part of my job, I guess. I think one point I'd want to make in that area is that there can be a bit of a tendency for the research community to look for solutions to problems where the light is shining, right? So classes of algorithms that run well on hardware that we have now is going to be where people tend to cluster. And I think one of the things that really excites me about products like the LightOn or this kind of BSP approach or things like that, people are going to start exploring different classes. I mean, so we saw ResNet, but imagine some very sparse and highly recurrent network that might not run very well on existing hardware, but would run well on this. That's a design space that the research community hasn't really attacked yet. So I think that, yeah, I can't say something will be future-proof, but I think we'll get a much faster taste of the future now with more hardware coming out.
Brilliant. Right, last quick responses, James and...
I think the answer is very clear. What hardware is more adaptable? It's proven out to be GPUs. It's empirically true because GPUs were first designed for gaming. They were extended through the CUDA language to work on a variety of HPC problems, everything from molecular dynamics to embody, and then now they work on deep learning. And when deep learning came around, they didn't just work on one deep learning algorithm. It worked on LSTMs, it worked on CNNs, it works on GANs. So deep learning is the basically general purpose programmable parallel processor, and any complex problem is kind of in that nature. So I think GPUs are actually proven out.
I accept that challenge. However, you will have noticed in my talk that I didn't really talk about deep learning or neural networks, because I don't think that it's all about deep learning or all about neural networks. Neural networks are very old technology. We only got excited about them since AlexNet 2012, because suddenly we had lots of data and lots of compute power to throw at them. I suspect a lot of other legacy ideas and a lot of ideas yet to come will also have a role to play. You will see lots of examples in this conference of neural networks working really well. You'll also see loads of examples of them falling over embarrassingly. So obviously they're not it. It so happens neural networks are more tensor-centric than graph-centric in my generic model. But a lot of other ideas are more graph-centric than tensor-centric. That's why the IPU is a graph machine and not a tensor machine.
Wonderful. Gentlemen, thank you very, very much. We've had some of the best chip designers from California and Paris and Avon. It's wonderful to have you all here. There is now going to be a Meet the Speaker session with our 4 panelists. Maria is going to take them downstairs, and you can follow her. It's downstairs and below this, where you can have some Q&A, and we have our final chat just before lunch. But thank you very much.